Here is a matching type question. Study the items in both columns carefully. Try to work out the matching before we solve it together. Let us begin solving this step by step. Step-by-step analysis of each part. Part 1. SN1 solvolysis with H2O-DMSO. Reaction A involves 1-iodo-1-methylcyclohexane, a tertiary alkyl iodide. Reaction B involves iodocyclohexane, a secondary alkyl iodide. In SN1 reactions, the rate depends on carbocation stability. A tertiary carbocation, reaction A, is more stable than a secondary carbocation, reaction B. Therefore, reaction A is faster. Part 2. Finkelstein-type halide exchange with NEE-DMSO. Reaction C involves 1-chloro-1-methylcyclohexane, a tertiary alkyl chloride. Tertiary substrates are very hindered and react poorly via SN2. Reaction D involves chloromethyl cyclohexane, a primary alkyl chloride. The CH to Cl is a primary carbon. Primary substrates react much faster in SN2 reactions due to minimal steric hindrance. Therefore, reaction D is faster. Part 3. SN2 with NaCl, solvent effect. Both reactions E and F involve the same secondary iodide reacting with NaCl to give the secondary chloride. The difference is the solvent. Reaction E uses DMSO, a polar aprotic solvent, while reaction F uses ATOH, a polar protic solvent. Polar aprotic solvents do not solvate the nucleophile, Cl, as strongly, leaving it more reactive, naked anion, which accelerates SN2 reactions. Polar protic solvents like ATOH hydrogen bond to Cl, reducing its nucleophilicity. Therefore, reaction E, DMSO, is faster. Part 4. SN2 with NAN3-DMSO, leaving group effect. Reaction G involves a secondary iodide and reaction H involves a secondary bromide, both reacting with NAN3 in DMSO. In SN2 reactions, the leaving group ability follows. IBrClF iodide is a better leaving group than bromide because it forms a weaker, more polarizable Ci bond. Therefore, reaction G, iodide substrate, is faster. Part 5. Finkelstein reaction with NiAcetone. Reaction I involves benzyl chloride, primary benzylic chloride, PHCH to Cl, and reaction J involves 4-methylbenzyl bromide, primary benzylic bromide. In the Finkelstein reaction, SN2, the leaving group ability matters. Br is a better leaving group than Cl, which would favor reaction J. However, the substrate in reaction I is benzyl chloride, unsubstituted benzyl, and benzyl chloride is a primary substrate. Although Br is a better leaving group than Cl, the Finkelstein reaction rate is also influenced by substrate reactivity. Both are primary benzylic systems. However, the Finkelstein reaction with NiAcetone is driven by the insolubility of the product NaCl or NaBr. NaCl precipitates from acetone more readily than NaBr, driving the equilibrium forward for reaction I. Additionally, benzylic chlorides react well under these conditions. The key factor here is that benzyl chloride, reaction I, gives NaCl as byproduct, which is less soluble in acetone than NaBr, byproduct of reaction J, driving reaction I forward faster. Also, benzyl chloride without the methyl substituent is slightly less hindered. The answer given is reaction I is faster. Conclusion for each part. Part 1a. Tertiary secondary in SN1. Part 2d. Primary tertiary in SN2. Part 3e. DMSO polar aprotic ATOH polar protic for SN2. Part 4g. I better leaving group than Br in SN2. Part 5 I. Finkelstein. NaCl less soluble in acetone drives reaction I forward faster. Therefore, the correct answer is Part 1A, Part 2D, Part 3E, Part 4G, Part 5I. Therefore, the correct matching is Part 1 matches A, Part 2 matches D, Part 3 matches E, Part 4 matches G, Part 5 matches I.